Let's look at the Pelton wheel, the primary example of an impulse turbine, operating on specific mechanical rules. First is how it handles the water's energy. The entire available energy is converted into kinetic energy before it hits the buckets. Because this energy conversion happens at the nozzle, the flowing water's pressure remains unchanged. As it moves across the runner, the pressure is equal to atmospheric pressure. To solve numerical problems for this system, you need to track a specific set of variables: the absolute jet velocity, the bucket speed, the force exerted, the resulting power, and 3 distinct efficiencies: hydraulic, mechanical, and overall. Standardizing your list of variables at the start ensures you don't misplace units during the more complex work-done calculations later. The absolute speed of the water jet doesn't dictate the force on the turbine. Since the bucket is moving in the same direction as the jet, we calculate the relative velocity. To find the initial relative velocity at the inlet, you subtract the bucket speed from the absolute jet velocity. This resulting vector is the actual speed of the water relative to the metal of the moving bucket. As the water glides across the bucket's curve and exits, it deflects at a specific angle. Mapping this exit geometry gives us the outlet velocity triangle, containing both the new relative velocity and the final absolute velocity of the exiting water. We construct these triangles because the vectors give us the horizontal components needed to calculate the force. You take the inlet and outlet whirl velocities from the geometry and plug them into the force and work done equations. Mastering the geometric mapping of these vectors provides the specific values required to prove the mechanical work of the system. Calculating work done depends on the direction of the outlet whirl velocity relative to the bucket speed. The sign convention is specific. If the outlet whirl velocity and the bucket speed point in opposite directions, you add their values. If they point in the same direction, you subtract. Pause the video for a second. Look at the bottom triangle. Use that sign convention to mentally plug a set of sample values into the hydraulic efficiency formula. When you graph out the hydraulic efficiency across different bucket speeds, a mathematical condition emerges. Maximum efficiency occurs when the bucket speed is half the velocity of the incoming jet. That 0.5 ratio dictates the physical design of impulse turbines. Engineers tune penstock nozzles and generator loads to maintain that speed ratio for peak output. In a comprehensive problem, we start with the net head, calculated by subtracting the losses from penstock friction from the gross head. This ensures the jet velocity calculation reflects the actual energy reaching the runner. If the problem asks for the number of jets required, you calculate the total discharge needed for the target power and divide it by the discharge capacity of a single jet. Watch the units. A correct velocity triangle won't yield the right answer if the rotational speed isn't converted from RPM into radians per second, or if the final watts aren't divided by 1,000 to get kilowatts. The final calculation targets overall efficiency. This verifies the entire chain of energy transfer, from the water power at the nozzle inlet all the way to the mechanical shaft power driving the generator. This summary contains the velocity triangle geometry and the 5 core formulas for the complete calculation set. Take a screenshot now. Solving these problems is an exercise in discipline. Reliability comes from consistent unit conversions and careful attention to vector sign conventions.